Consider the following problem. Suppose we are given a circle of radius r. How many points with integral coordinates could lie inside this circle? To make this more precise, let's use the following notation: n of r to denote the number of points with integral coordinates that lie inside this circle. So this circle is centered at the origin. Some of you might be interested to know what happens if we include the points on the perimeter. So let us include that case as well. So we use the notation nr tilde to denote the number of integral points lying inside of the circle and on the perimeter of the circle. Or rather, I should call this a disk. When looking at this problem, some of you may have a feeling that the number of points inside of the circle, including the points on the boundary or not, should be somehow related to the area of the circle. So you may have the feeling that n of r and n bar of r should be approximately the area of the circle. But mathematicians are interested to know what the area of this approximation is. Namely, if you take the absolute value of nr minus pi r squared, or the absolute value of n tilde r minus pi r squared, how big could those differences are? What we are going to do now is that we are going to show that this error is actually equal to the big omega of r. Remember, this notation means this is bounded above by some absolute constant times r. This is due to Gauss, so this problem is called the Gauss Circle problem. So now let's start giving a proof of this. First, let's just focus on the first guy, namely the difference between pi r squared and the points that lie inside the circle, excluding the points on the perimeter of the circle. So let's try to give this an estimation. The method we use for this estimation is very classical in mathematics. In order to count the points in the region, what we do is that we are going to divide this region into some small blocks, where each block contains precisely one point, and each block has the same area. So instead of counting the number, we are going to count the total area of those small blocks. And if you take the union of those small blocks, the union forms a new region, and that region will have some sort of shape. And you calculate the area of that shape, and you divide that shape by the area of each small block. That gives you some estimation of the number of the blocks, and thus the number of points, because each block will contain precisely 1 point inside this region that we want to count. So that is the idea. So maybe let me quickly write down the idea. So the idea is the following. You first divide the region into small blocks with equal areas, with each of them contains precisely 1 point. The small blocks form the new region, whose area is easier to estimate. And then you divide the area of your new region formed by blocks by the area of each block. And that is the estimation for the total number of the points that you want to count in the original region. So now let's carry out this idea. In the first step of our idea, we want to divide the region into small blocks with equal areas, with each of them contains precisely 1 point. What we are going to do in this situation is that we're going to use the blocks consisting of squares of set length equal to 1 centered at those integral points. That is the most natural choice for us. So let me write this down carefully. So we consider the collection S of the squares centered at the integral points with side length equal to 1. We consider all such squares. If we draw this in this graph, maybe squares like this. I'm not going to draw all of them. So this is not very precise, but I hope at least you understand that those squares are centered at the integral points with side length 1. There will also be squares outside of this circle. So I'm not going to draw all of them. So you know there are squares everywhere centered at the integral points. So now let's give an estimate of this. We claim that this absolute value is bounded by the maximum of the following two things. First, the number of squares in this script S that are contained in this disk of radius r. Remember, this n of r does not include the counting of the number of integral points on this circle. It only counts the number of integral points inside of this circle. So this should be an open disk. And we look at the difference between this number and the area of our disk or circle. So this absolute value we bound it either by this absolute value or the following that I'm going to write. The number of squares in S such that each of them has non-empty intersection with this disk. Namely, we are going to count the squares like this. If you do the high school geometry a little bit more carefully, you will see this square also has a non-trivial intersection with this circle. Although I didn't draw this very precisely. That is because the boundary in here is convex outwards. And we are going to take the difference of this number with the area of the circle. That is the second number. And we take the maximum of those two numbers. And I claim that this maximum is greater or equal to this difference. Do you see why? This is because if you just look at n of r, the number of points inside of this circle, because of our construction of those squares, this number will be greater or equal to this number. But at the same time, this number is also less than or equal to this number. So you know that this absolute value is bounded above by the maximum of those two absolute values. That is how you find the maximum of the absolute value of x minus some constant. We just look at two boundary cases. Now here's the interesting thing. Because that we take each square to be of set length 1, the area of each square is 1. So the number of squares will be same as the area of the union of those squares. So this number will be same as the area of the union. That is important. That is going to be used in our next step. So now we claim that the maximum in our second line is again bounded above by the following quantity. It is bounded above by the area of the circle with radius r plus square root of 2 square. It is bounded above by the difference of the area of the square of radius r plus square root of 2 and the area of the circle with radius r minus square root of 2. The explanation of this might be a little bit tricky. So let me try to convince you of this. So this circle has radius equal to r. And now let's draw circles of radii r plus square root of 2 and r minus square root of 2. So this is a circle of radius r minus square root of 2, and this is a circle of radius r plus square root of 2. And let me try to explain this inequality. So what we are going to do now is that we are going to find the boundary of the union of the squares that are contained in this disk, in this open disk, as well as the union, the boundary of the union of those squares which have non-empty intersection with this open disk. The boundary of the first union can be plotted like this. So this region will be the union of the squares contained in this open disk. And now let's look at the other one. So this is the boundary of the region formed by the union of the squares that have non-empty intersection with this open disk. There might be some inaccuracies in my drawings, but I hope this idea should be clear to you. Now here is the observation. The observation is that if you look at the area that is squeezed between those two blue boundaries, namely this part, that area is actually equal to the summation of those two differences. And in particular, it is bigger or equal to the maximum of those two differences. So this maximum is bounded above by the area between two blue boundaries. And this area is again bounded by the area squeezed between those two green circles, namely the area of this annulus, which is precisely the pi times r plus square root of 2 raised to the power 2, which is precisely pi times r plus square root of 2 squared minus pi times r minus square root of 2 squared. This is true because if you look at each square in this outer blue region, for example, if you look at this square, because it has non-empty intersection with this disk of radius r, and because this outer circle has radius r plus square root of 2, this square cannot touch the outer green boundary. That is why this outer blue boundary is actually contained in this outer green circle. Likewise, if you look at any square that is not in this inner blue region, say if you look at this square, because of our choice, because this square is not in this set, this square is not contained in this open disk, then this square has to touch this circle of radius r. And because this inner circle has radius r minus square root of 2, by two-dimensional geometry, since the diagonal has length square root of 2, you know that this square cannot touch this inner green circle. And now if you look at the whole boundary of this inner blue region and consider all such squares, none of them could touch this inner green circle. It follows that this inner green circle must be contained in this inner blue boundary. So, this shaded blue region squeezed in between has area bounded by this annulus, which is precisely this. Now what is this difference? This difference is equal to 4 times square root of 2 times pi r, if you compute it. And this tells you the error is actually a big omega of r. So finally we get the result we want. So this completes our estimation of this. And now, how about this intuitive form, which is the number of integral points inside the circle, including the boundary, the perimeter. Namely, we are interested to know what is the estimate of this guy. So we want to estimate this. What changes do you think we need to make in our argument? I'll let you think about it for a while. The only change that I think we need to make is that we want to take the closure of this open disk in here in order to provide a more generous bound. Although this guy may not be bigger than the guy without this tilde. Everything else will be the same, because when you consider the points on the boundary of this radius, on this circle of radius r, in here you also want to consider the squares that has non-trivial intersection with this disk, including the boundary. That is the only difference. And everything else will be the same. And the final result will also be the same, because anyway, you're computing the difference between the areas of two circles. You're computing the area of this annulus. So this estimate is still the same, and the area you get is still the same. And that completes this estimate. I should add a remark that our estimate only holds for the case when r is greater than square root of 2. Because when r is equal to square root of 2, this inner circle doesn't make sense. And actually, in that case, the estimation of the points, the integral points contained in the circle will be trivial, because that radius of this circle is just a very small number which is bounded by square root of 2. And you can easily check how many points are there in that small circle. So what does this estimate tell you? So in the end, I want to emphasize that this estimation tells you when the r goes to infinity, because the r square will become much, much bigger than r, which dominates our estimation, in which case this big omega r can be ignored. So when r is very big, you know that the number of points inside this circle of radius r, with or without boundary, is roughly pi r squared. And that is the beauty of this Gauss circle problem.